Good evening, my name is Araujo Dantas, and I'm going to start the presentation of the Advanced Topics in Engineering project. And that is also my undergraduation final project, so I'm still doing it, I'm still working on it. The theme of this work is the direction of arrival estimation using directional antenna array for detection of UAV signals. UAVs stands for Unmanned Aerial Vehicles, that is also known by drones. Here is the outline of this presentation, that will follow this flow: the motivation, the state of art, the proposed model, the simulations, next step, and the references that I was based on to do this work. First, the motivation. The main motivation of this work is the increase of the risk generated by the manipulation of drones. Since drones have become a very popular product in the market, we had an increase on the numbers the increase of the numbers of the manipulation of these vehicles, these aerial vehicles. So with the increase of the numbers of products on the market, we had an increase on the risks generated by the manipulation of these drones, especially on airports, stadiums, and penitentiaries. On airports, the risk is the collision between the drone and the aircraft while the aircraft is landing or arriving in the airport. In the stadiums, since we have a lot of people together, we can cause an accident by hurt someone. And in the penitentiaries, we have the risks of the use of the drone to get things in the penitentiary or to get things out of the penitentiary. That is not legal. So the main risk of this project is the main motivation of this project is to try to reduce the risk of the manipulation of these drones. The state-of-art model is a model based on the differences between the received signal strength at each antenna. The received signal strength can be calculated by the phase transmission equation that I will explain later. But first I have to explain that in this project I'm going to use an antenna array. So why this is the model that I was based on? It's because we have each antenna, for each antenna we can calculate the received signal strength, and then we can proceed with the evaluation of the differences between these RSS at each antenna. So the phase transmission equation is described by these terms here. Here is the RSS that will be calculated. Here is the power of the transmission. Here we have the gain of the transmission. And here we have the gain of the directivity gain of the antenna. And here we have the speed of light. R is the distance between the receiver, that is the antenna, and the source, that is the drone, and F is the frequency of the transmission. Then after we use this equation to calculate the RSS, and after the evaluation of the differences between the RSS at each antenna, we can estimate the direction of arrival using the multiple signal classification algorithm, that is the MUSIC. So that is the state of the art. Now I'm going to present the proposed model. The proposed model uses the RSS evaluation tool. So the estimation of the direction of arrival is the direction of arrival is estimated using the received signal strength at each antenna and the directivity gain pattern of each antenna. The directivity gain pattern is a characteristic of the antenna, and it describes to which direction the antenna receives better the signal. So the model is, we evaluate the differences of the received signal strength at each antenna, and then we transform this. We take these differences and we vectorize these distances, this received signal strength, sorry. Then we proceed with, we do the same thing to the directivity gain patterns. We evaluate the differences between the directivity gain patterns of each antenna, and then we vectorize this. So we have a vector of the RSS and we have a vector of the directivity gain pattern. Then we proceed with a Euclidean distance evaluation between these two vectors, and we have then we maximize it. So we can get as a result the spatial power response, that is the estimation of the direction of arrival. So that is the proposed model. Now I'm going to present some simulations here. First, this is the directivity gain pattern of one antenna. The values of the gains were taken of the specification of the antenna. And here we can see the received signal strength at one antenna. So here we can see that the pattern is very similar of the RSS at one antenna to the directivity gain pattern of this antenna, just the values here changes. Here we can see the spatial power response, that is the estimation of the direction of arrival. So since here we have the RSS at 0, we can see that the direction of estimation is marking here 0.2, so we can calculate the error, the absolute error of this estimation. And here, as we can see, we calculated the absolute error from minus 90 degrees to plus 90 degrees. So we can see that since this is the received signal strength, this is the pattern of the received signal strength, that's the curve, and here is the curve of the directivity pattern gain. We can see that this antenna receives better when the direction of the signal is on 0 degree. And here we estimated the 0.2, and here in the absolute error we can see that here we can see that the line is low. We have short values here, low values here. Here we can see the root mean square error for the angular spacing, and the angular spacing is the spacing between the antennas. So after some calculations and tests, it was proved that the best angle is, as we can see here in this curve, is between 35 degrees and we can say 65 degrees here, because it presented a lower RMSE, that is the root mean square error. So the next step that I'm going to do, and the next part of this work, will be the field experiments. And I'm going to use a antenna array with 4 Yagiud antennas. That is the antennas that have this directivity gain pattern here. I'm going to use 4 of them, and the angular spacing that I'm going to use will be 40 degrees. And then as the next step, we can proceed the same experiments that I'm going to do with the 4 Yagiud antennas. I will do the same experiments with the patch antennas. And that's the references that I use to this work, and that's it. Good evening, thank you.